My name is Maimun Farhan Khan. My ID is 242333051 and I am from section B. Today I am going to be exploring a fascinating subject of resonance circuits. So without further ado, let's dive into it. Have you ever turned on a radio to just the right frequency and the music starts sounding crystal clear? That's resonance at work. This presentation will explain what resonance circuits are, how they work, and why they matter. Let's first of all understand what is resonance. Resonance is a phenomenon that occurs when a system is driven at its natural frequency, resulting in a significant increase in amplitude. In simpler terms, when an external force or signal matches the frequency or the system's natural frequency, the system oscillates with maximum energy. If we were to give an example, imagine a swing that is swinging at its own natural frequency, and just at the right moment, someone gives an outer force just at the right moment. And then we see that the swing just goes higher and higher. That is resonance in action, where the applied frequency from outside matches the swing's own natural frequency, increasing its amplitude. In case of electrical resonance, it occurs when inductive reactance is equal to that of capacitive reactance. Now, let's understand some frequency basics. What is frequency? Frequency is basically the number of oscillations per second measured in hertz. There is also angular frequency called omega, which is 2 pi times of the frequency, and it's useful in case of AC circuit analysis. As to why it matters, in RLC circuit, inductors and capacitors behave differently depending on the frequency. Frequency determines whether a circuit acts like a resistor, capacitor, or inductor. Resonance results when where the imaginary part of the transfer function is 0. Now let's come to the fundamental part of understanding resonance circuits. What resonance circuit is? A resonance circuit is an electrical circuit consisting of resistor, inductor, and capacitor, just as the name suggests, where resonance occurs when the inductive reactance is equal to that of capacitive reactance. The reactances cancel each other out, the circuit's impedances becomes purely resistive, and voltage and current are in phase, thus power factor becoming 1, and energy is continuously oscillating between the inductor's magnetic field and the capacitor's electric field. From the figure, we can understand it better, so let's go to the next slide. Here we can see a vector diagram of an RLC circuit. We will focus on the fourth one, where we see that XL is equals to XC. Basically, the inductive reactance is equal to that of the capacitive reactance. Now, if we were to measure the net reactance, we see that net reactance here is 0, and what we are left with is just Z impedance, which is equals to that of resistance. What that means is that there is no net reactance. The circuit behaves like a pure resistor that we foretold before. No phase difference between the voltage and current. They are in phase angle is 0, therefore the power factor is 1. Maximum power is transferred to the circuit during this moment. Now, jumping back to the previous one, how is an RLC resonance circuit formed? An RLC circuit, resistor, inductor, capacitor one, is built in either series or parallel configuration. When the frequency of the input signal matches that of the natural frequency of the LC combination, resonance occurs, which we express with the formula F0 equals to 1 by 2 pi root LC. Now let's jump on to the working principle. Just as we foretold, inductive and capacitive reactances cancel each other out. Impedance is minimized in case of the series circuit, and impedance is maximized in parallel circuit. Current and voltage are in phase, and the power factor is 1. Energy oscillates between capacitor's electrical field and inductor's magnetic field. Now let's jump into the slide where I am showing a parallelism between different features of series resonance circuit and parallel resonance circuit. We have configuration, resonance frequency, resonance condition, impedance at resonance, there is voltage, power factor, phase angle, etc. etc. Now let's jump to the next slide. Applications. There are many applications of resonance RLC circuit. We are going to be going through them one by one, and we are just going to go through each of them. Radio tuning, how it works. When one tunes a radio station, they are adjusting the LC circuit to resonate at the frequency of that radio signal. and only the signals at that resonant frequency are amplified while the others are filtered out. This is an application of series or parallel LC circuit as a bandpass filter. Next, we have TV channel selection. TV channels also use resonant circuit to pick up certain frequencies assigned to those channels. Each channel has a different frequency and the circuit resonates to pick one at a time. There are metal detectors. In metal detectors, resonant LC circuit is used that detects the change in inductance caused by nearby metal. When a metal comes near, the resonance condition shifts, triggering detection. Wireless charging system. Wireless chargers use magnetic resonance to transfer energy from a charger to device without wires. Both coils, charger and the device are turned to resonate at the same frequency for maximum efficiency. There is MRI machines. MRI uses nuclear magnetic resonance. A specific resonance frequency of hydrogen atoms are excited using a magnetic field, producing a detailed internal image. Filters in audio equipment. Audio equalizers and tuners uses resonant bandpass filter to amplify or suppress certain frequency bands, bass, treble, etc. There is a summary on its application, at which sectors it is used and how it is used. Now coming to the key takeaways on resonance circuit. Resonance is a fundamental phenomenon that occurs when inductive and capacitive reactance in a circuit cancel each other out, leading to a purely resistive impedance at specific frequency. Resonance circuits, especially series and parallel RLC circuits, are powerful tools for frequency selection, filtering signals, efficient energy transfer. The resonant frequency is determined by the value of inductance and capacitance. The quality factor and bandwidth help measure how sharp or selective the resonance is. It is key in designing filters and tuners. Resonance isn't just a theory, it's used across electronics, medicine, telecommunications, and more. Understanding resonance means understanding how a system naturally behaves and how we can harness that behavior in order to control, filter, or amplify what matters the most to us. Thank you for being a part of my presentation.